Tonight we're exploring the slow, breathing giants of the Earth, volcanoes. We'll journey deep beneath the crust to see how molten rock is born, how eruptions shape new islands, and how even destruction gives way to creation. You'll learn about fire meeting ice, mountains that sleep for centuries, and the quiet beauty left behind once the lava cools. Now, take a deep breath. Let your thoughts settle like ash after the storm. And together, let's drift into the heart of the earth, where fire breathes and silence begins. Under the crust, in a place most of us never see or feel, something patient and relentless is underway. Imagine a vast, slow kettle of the planet's innards, rock so hot it behaves like a thick, stubborn syrup. That's magma. It forms where rock melts deep in the mantle because of temperature, pressure changes, or the addition of water and other volatiles. When conditions tilt even a little, the balance breaks and the magma starts to move, searching for a path upward. Think of it this way. You felt pressure build in your chest when you're holding your breath or trying to keep something in. Magma does the same thing. As more heat and melted rock collect, pressure climbs. It's not loud or dramatic at first. It's the slow loading of a spring. Eventually, that pressure finds a weakness, a crack, a fault, a boundary between tectonic plates. Those tiny openings are invitations. The magma forces its way through, sometimes inching along fractures as magma-filled veins called dikes, sometimes pooling into chambers where it can sit for years, decades, or millennia. Those magma chambers are like attic rooms where the planet stores its heat. They're not always full. Sometimes they're mushy mixes of crystals and melt. But when enough melt accumulates, the system becomes restless. Gas plays a huge role here. Magma contains dissolved gases, water vapor, carbon dioxide, sulfur compounds, held under the weight of overlying rock. As magma rises and the pressure drops, those gases come out of solution, forming bubbles. Bubbles expand. Bubbles increase pressure. Pressure drives magma faster. That interplay of melt and gas is a primary reason eruptions can switch from lazy, flowing lava to explosive, ash-throwing events. Different settings make different volcanoes. At plate boundaries where plates diverge, like mid-ocean ridges or continental rifts, decompression melting produces magma that's relatively fluid. That's why eruptions there can be gentle, with rivers of basaltic lava slowly covering the land. Where one plate dives under another, subduction zones. Water dragged down lowers the melting point of mantle rocks, producing magma richer in silica and gases. Those magmas are stickier and prone to explosive behavior, building tall, cone-shaped stratovolcanoes. And then there are hotspots, plumes of hot rock rising from deep inside the mantle, creating island chains like Hawaii when a plate drifts over a steady source of upwelling magma. When magma finally reaches the surface, it's releasing more than molten rock. It's exhaling ash, gas, and molten stone, like the planet taking a deep breath out after holding it for ages. Sometimes that exhale is a slow sigh, lava oozing in glowing streams, reshaping shorelines and fields. Sometimes it's a violent cough, columns of ash shooting miles into the sky, cloaking towns and changing weather. And always, after an eruption, the landscape is altered. Valleys are filled, new land is created, and the chemistry of soils changes, often making them richer and more productive over time. You can relate to this because we live with pressure and release in our own lives. A long stewing worry can finally find a way out in a conversation that changes everything. A trapped feeling might push you to take a new path. Volcanoes remind us that pressure needn't be purely destructive, it can be transformative. They are Earth's way of balancing the immense heat hidden within, redistributing energy and material from deep inside to the surface. And there's a humble beauty in that honesty. The planet doesn't pretend it's stable all the time. It breathes, it shifts, it remakes itself. That knowledge changes how we think about danger and opportunity. People who live near volcanoes know this intimately. Their towns are shaped by past flows, their fields fed by volcanic soils, their stories braided with eruptions and rebuilding. Volcanoes are born in the dark, slow engines beneath us, but their life is written in ash on the wind and new ground under our feet. There's something almost mesmerizing about a river of molten rock. Picture this. Dusk has fallen. Everything else is a silhouette, and out of the dark a long orange vein crawls across the slope. It pulses. It breathes. Up close you can feel the heat wrap around you like an invisible blanket. That glow, the deep, living orange, is not light the way a lamp is light. It's the light of something alive and furious, a material that used to be rock and has been unmade and remade into motion. Lava is simply molten rock, the same stuff under your feet, but melted and set loose. Temperatures can exceed 1,000 degrees Celsius, and that makes behavior interesting. Not all lava moves the same. Some of it oozes, barely shifting hour to hour, folding into smooth ripples that cool into rope-like patterns. Other lava charges downhill, racing like a burning freight train that eats everything in its path. Both ways of moving tell you something about how sticky the melt is, its gas content, and the slope it's moving down. If you've ever seen photos of Hawaiian eruptions, you've glimpsed two very different personalities of lava. Pahoehoe, pronounced Pahoehoe, is the one that moves more slowly, spreading in sheets and forming those beautiful swirled, ropey surfaces. When it cools, you get that rippled stone that looks like waves frozen in time. The surface can crust over while molten rock still slides inside, so one minute it looks solid and quiet, and the next there's a small break, and lava oozes out like toothpaste. It's easy to imagine running your hand along the gentle folds, except you would never, because of course it's still hot enough to bake you. Then there's Oa, which is rough, jagged, and moves more forcefully. It breaks into loose, clattering fragments that tumble and tumble as the flow advances. Because it's broken and clinkery, AA flows look more chaotic, more destructive, and often they do move faster across steeper terrain. Underlying both is the chemistry of the melt. Basaltic lavas, low in silica, are more fluid and tend to travel farther. Lavas high in silica are sticky, slow to flow, and more likely to pile up or explode. Those differences are why some eruptions paint the landscape with long flowing ribbons of lava, while others build steep domes and send ash skyward. Watching lava flow, whether in photos, videos, or from a safe viewing distance in person, can feel like watching nature's editing process. As the flow loses heat, a crust forms on top. That crust acts like an insulating blanket, keeping the inner core molten and allowing lava to travel surprising distances. In some cases, the crust thickens into a tunnel and the lava keeps moving inside. When the flow finishes, that tunnel drains and you're left with a lava tube, a hollow conduit, silent in the daylight, that once pulsed with red-hot rock. Those tubes can be walked through long after the eruption, strange, cool caves that are the memory of movement. The moment lava finally gives up its heat, it becomes solid land. The transformation is dramatic in human terms. A place that was empty or vegetated becomes black, hard stone that will not easily be moved. If the flow met the ocean, the result can be new shorelines and even islands. That's how places like the Hawaiian chain keep building out. Each eruption lays down new layers that, over time, become part of the map. Standing on a fresh flow, you're standing on something both made and destroyed by the same force. The silence of cooled lava feels almost reverent. It doesn't beg forgiveness, it simply becomes. There's a kind of humility in that, loss and creation braided together. It's natural to think of lava only as the agent of ruin. Houses covered, forests burned, roads erased. But there's another story too. Those fresh surfaces create new ground for life to colonize. Lichens and mosses are the first to stake a claim, then grasses, then shrubs and trees. Geological time is patient. What looks like a wasteland in year one becomes, decades and centuries later, a new habitat. So the molten river that flattened a valley also set the stage for a new one. For people who live with volcanoes, that cycle is woven into daily life, caution and respect for the immediate danger, and a longer, older gratitude for the land that gets remade. On a personal level, that mixture of terror and awe is hard to shake. I remember watching footage where the camera lingered on a lava flow as it slowed and sighed into a field. You could hear the crackle, the occasional pop as gas escaped, and then the sound dropped away. The frame filled with those orange veins cooling to black. It felt oddly like watching someone finish a piece of sculpture, messy and violent, and then suddenly quiet and complete. If you've ever stood on a hill and watched a sunset smooth the world below, imagine that on a volcanic scale, heat and light, and then the inevitable hardening into the next landscape. Molten rivers are more than spectacle. They are active physical reminders of a planet that changes, often dramatically. They teach us about extremes, heat, motion, chemistry, and about time. Destruction happens in an instant compared to the slow work of rebuilding, but rebuilding does happen, even if it's measured in rock and roots and generations. Next, we'll look at how those cooled flows record the story of an eruption, the layers, the textures, the clues a rock gives you about its fiery past. Think of volcanoes as personalities, not just cones of rock, but living characters with their own temperaments. Some are the calm, steady types. Others are dramatic, unpredictable performers. The differences come down to what's happening deep below, the chemistry of the magma, how easily it flows, and how it escapes to the surface. Those factors shape not only how a volcano looks, but how it moves and how communities around it learn to live with it. Take shield volcanoes. Picture the broad, low domes of Hawaii, not towering pyramids, but gentle giants that spread outward like a slow-spreading blanket. Their lava is runny, basaltic, and low in silica, so it pours and pools instead of exploding. When a shield volcano erupts, it feels almost patient. Long, fluid streams of lava inch across the land, creating rivers of light at night, and building wide platforms over decades and centuries. Standing on cooled black rock that was once molten, you can almost feel the scale of time. Eruptions that last weeks or months, sometimes years, but with a message more of creation than catastrophe. They reshape coastlines, create new land, and leave behind landscapes that invite walking and exploration rather than sudden evacuation. That slow, rhythmic behavior is what gives shield volcanoes their heartbeat. It's a steady thump. Magma rises, pressure is released through steady flows, and the volcano settles back down. For people who live nearby, the rhythm can become part of daily life. A distant glow on the horizon, a smell of sulfur after a wind shift, or the cautious thrill of watching new black rock swallow a field. There's awe, yes, but also an intimacy with change. Farmers learn which plots will be improved by fresh volcanic soils. Communities build livelihoods around the land these volcanoes create. Now switch scenes to stratovolcanoes, the classic cones that dominate postcards, rising tall with steep, jagged profiles. These are built from alternating layers of ash, pumice, hardened lava, and rock debris. The magma feeding these volcanoes tends to be thicker, richer in silica. That stickiness traps gases as magma tries to rise. Pressure builds, sometimes for years, until it releases in an explosive act. When stratovolcanoes erupt, they do it with theater. Towering ash columns, glowing pyroclastic flows that roar down slopes, and showers of hot rock and ash that reshape entire valleys. Their heartbeat is different. Longer periods of quiet, punctuated by sudden violent beats. That unpredictability fuels both fear and fascination. For towns around these volcanoes, the relationship is more cautionary. Fertile soils and stunning views come hand in hand with evacuation plans and hazard maps. The memory of an eruption can linger in the culture, stories passed down, changes in settlement patterns, and a heightened respect for the mountain's moods. And there are other voices in the volcanic chorus. Cinder cones are the smaller, spikier relatives, often short-lived. They build quickly from ejected fragments and then go quiet. Lava domes form when very sticky lava piles up over a vent, creating steep, unstable mounds that can collapse and produce dangerous flows of ash and rock. Each of these types has its own tempo and its own signature on the landscape. What ties them together is a sense of deep calm that can hide intense energy. Whether a volcano is pouring lava like a slow heartbeat or storing pressure for a dramatic outburst, all of them are ways the earth breathes. That image, the planet inhaling and exhaling over geological time, helps make sense of why people become so attached to and so careful around these places. If you've ever stood near a volcanic slope, you know there's a tension between beauty and risk. You can appreciate the soft curve of a shield volcano and feel the raw power in a stratovolcano's silhouette at the same time. And that duality shapes how communities adapt, building with the landscape's gifts, preparing for its moments of fury, and learning to read the subtle signs when the Earth's heartbeat quickens. Next, we'll explore how scientists tune into those beats, the instruments and observations that help translate a volcano's rhythm into warnings, forecasts, and a deeper understanding of the forces that shape our world. If you close your eyes and picture a volcano, you probably see a cone of fire on a mountain, lava flowing down, ash in the sky. Now flip that image. Imagine that same rumble, that same heat, happening under miles of ocean. It's harder to picture because we don't live there. But down below the waves, volcanoes are not rare oddities. They form a continuous, hidden landscape that shapes the planet in ways that are quietly dramatic. Start with the mid-ocean ridges. This is a global seam where tectonic plates pull apart and molten rock, magma, wells up. It's not a single line, but a network of ridges that snakes for roughly 65,000 kilometers around the globe. New seafloor is born here, inching away from the ridge like a conveyor belt. That slow, relentless creation is what keeps the ocean floors young compared to continents. Picture molten rock squeezing through cracks, cooling into basalt, and sealing the crust together. An invisible construction site building the very bed we float on. Near those cracks, where magma meets seawater, something else happens that feels like science fiction. Hydrothermal vents form, fissures that spew mineral-rich, superheated water. Because of the intense pressure miles underwater, water around these vents can reach temperatures of 300-400 degrees Celsius without boiling. The hot fluid mixes with cold seawater and precipitates metals and sulfides, building chimney-like structures that glow black or white. Sailors once called them black smokers, but their appearance is only part of what makes them extraordinary. What's really remarkable is the life that gathers around these vents. In absolute darkness, no sunlight at all, entire ecosystems thrive. Instead of plants turning sunlight into energy through photosynthesis, microbes here perform chemosynthesis. They take chemicals like hydrogen sulfide and oxidize them, using the energy released to build organic matter. It's basic chemistry, but the consequences are profound. Vast communities of organisms can exist without ever seeing the sun. If you picture a garden, think of clusters of tube worms the size of your forearm, standing like stalks, their feathery red plumes filtering the chemical-rich water. These worms don't have mouths in the way we do. Inside them lives a symbiotic army of bacteria that feed on the vent chemicals and, in return, nourish their host. There are also giant clams, shrimp that seem to glow, and mats of microbes carpeting the rocks, organisms so specialized that they've adapted to survive extreme temperatures, crushing pressures, and toxic chemistry. Many have no eyes. Color and light are irrelevant. Their lives are a lesson in how adaptable life can be when the rules change. The first time humans saw one of these communities was only in 1977, when a deep submergence vehicle called Alvin explored the Galapagos Rift. The sight was astonishing. Life in the most unlikely place, clustered around black chimneys, dense and teeming. That discovery rewrote assumptions about how and where life can exist. Since then, scientists have found vents across ocean basins, each hosting its own cast of specialized creatures. There's a very human reaction to all of this. For me, learning about hydrothermal vents felt like discovering a hidden city beneath the sea, one that runs on chemistry instead of sunlight. It makes you reevaluate how fragile and creative life is, and it sparks a kind of humility. We tend to measure habitability by our own yardstick: sunlight, temperate air, familiar conditions. But the ocean's secret world shows there are many other yardsticks that work just fine. That realization carries practical weight too. Studying vent organisms has already led to breakthroughs. Enzymes adapted to extreme conditions, new antibiotics, and insights into how life might exist on other worlds. When NASA looks at icy moons like Europa or Enceladus, the idea that life could survive in subsurface oceans warmed by tidal forces and chemical energy comes straight from what we learned at hydrothermal vents. At the same time, there's a tension brewing between curiosity, conservation, and commerce. Those mineral-rich chimneys hold deposits of copper, zinc, and rare metals, resources companies have started to covet. Deep-sea mining could disturb these fragile communities before we fully understand them. Imagine ripping up a rainforest to mine a mineral vein, except it's a forest that's been hidden in the dark for millennia. The consequences are unknown, and that's unsettling. So, when you think about volcanoes now, give a nod to the ocean's secret world. Beneath the surface, Earth is alive with molten motion and chemical alchemy. Life doesn't just cling to the light. It finds a way to harness whatever energy is available. That's both a scientific wonder and a personal reminder. Our planet holds surprises whose value goes beyond immediate use, and they deserve both our curiosity and our care. Think about the last time you watched a sunset and felt like someone had painted the whole sky just for you. Now imagine that pigment came not from a brush, but from a mountain that had just blown its top. When volcanoes erupt explosively, they don't only reshape the land, they reach up and exhale into the sky. Tiny shards of ash and clouds of gas are hurled high into the atmosphere, and some of that stuff gets stuck up there for months, or even years. That's when the sky starts to remember the fire below. It's strange how something so violent can feel intimate. I remember standing on a quiet street after news of a distant eruption and noticing an odd haze, a thin grit on my car, like the world had caught a memory of smoke. Friends texted photos of outrageous sunsets, streaks of crimson and deep violet that made ordinary evenings feel cinematic. It's easy to think of ash as only a hazard, but it also rewrites light. Those tiny particles scatter and filter sunlight in ways that favor long wavelengths, so the blues fade and the reds sing. The result? Sunsets that look like the earth is smoldering softly at the horizon. There's a simple science behind that visual poetry. When a volcano injects ash and sulfur dioxide high enough, chemical reactions in the atmosphere turn some of that sulfur into sulfate aerosols, microscopic droplets that reflect and scatter sunlight. Unlike the everyday dust that sits in the lower atmosphere and washes out quickly, these aerosols can ride the stratospheric currents. They travel, they spread, and they linger. Big eruptions can shave measurable fractions off global temperatures for a year or two. Mount Pinatubo in 1991 cooled the planet by about half a degree Celsius for a couple of years, because those aerosols reduce the sun's warming power. That chill in the air, if you could feel it at the time, was the planet breathing out ash, as if sighing after a fever. Historic eruptions give the effect an almost mythic quality. In 1816, after Tambora, people in Europe and North America called it the year without a summer. Frost in June, failed crops, and hungry communities all trace back to particles and gases that had circled the globe. And yet, Amid the hardship, artists and poets recorded sunsets so intense they seemed otherworldly. Krakatoa in 1883 produced blood-red skies seen thousands of miles away. Those visuals seeped into culture, a reminder that even disaster leaves an aesthetic fingerprint. On a human level, ash in the air complicates ordinary life. It's gritty under your nails, it stings your throat, it fouls engines. I've stood beside people who, after months of ashfall, still savored the burned orange sunsets, as if nature's display was a small consolation. For some, those skies became a way to feel connected to something vast, a distant rumble, a shared sky, a visible trace of an event they hadn't witnessed in person. For others, it was a warning, a reminder that the ground they walk on is alive and capable of sudden change. There's also a strange comfort in that juxtaposition, chaos and beauty braided together. Seeing the sky painted from an eruption makes the planet's systems legible in a way daily weather rarely does. You can watch the consequences unfold across hemispheres, ash drifting along jet streams, sunsets intensifying on the other side of the world. It's a humbling demonstration that what happens underfoot can alter the view overhead. So next time you stare at a particularly dramatic sunset, take a moment to imagine the story behind the hues. Maybe it's just pollution and humidity, but maybe, once in a while, it's the sky remembering the fire below. A long, slow inhalation and exhalation of ash and air, folding the memory of an eruption into the light that colors our evenings. That's the planet speaking in a palette we can understand, if we know how to read it. Take a stroll with me along a mountain trail. At first glance, the volcano is unassuming, its flanks a patchwork of moss, pines, and terraced fields. Children fly kites in its shadow. Farmers plant sweet corn on the lower slopes. It feels like any other hill in the countryside. That calm is what makes dormant volcanoes so deceptive. They look like old giants who've finally gone to sleep, but sleep, in geological terms, can be very long and very deep. I remember standing beneath one of these green slopes and feeling a strange mix of comfort and unease. On the surface, there's life everywhere. Birds, lichens on rocks, the smell of damp earth after rain. Underneath, though, the ground is still warm. Deep down, miles beneath our feet, the crust holds heat and molten rock that haven't entirely cooled. Dormant doesn't mean dead. It means patient. It means the plumbing of the mountain, the magma chambers, the gas pockets, the network of cracks and conduits, is quiet for now, but not forever. Think about the idea of pressure in your own life. We wait for a deadline, for a conversation, for something to happen. Sometimes we hold everything in, and then one small trigger, a text, a knock at the door, sets off a rush. Volcanoes are the same. They can rest for centuries, even millennia, building up tiny changes that eventually push them toward activity. A small influx of magma from deep in the earth, a shift in tectonic plates, or the slow accumulation of volcanic gases can tip the balance. That perfect breath of pressure, arriving at the right place at the right time, is what wakes them. Communities living around these mountains have stories that reflect this patience. Grandparents talk about crops that grow unusually well in volcanic soil, and also about relatives who left long ago when the mountain grumbled. The land is fertile because of past eruptions, The same eruptions that shaped the valley are what made it possible to farm there. People build lives in the shadow of a risk they've learned to live with, often carrying a quiet respect for the unpredictable nature of the land. From a scientific viewpoint, dormant sits between active and extinct. Active volcanoes are currently erupting or show ongoing unrest. Extinct ones are believed unlikely to erupt again. Dormant sits in the uneasy middle. Inactivity now, but the potential remains. How long does that potential last? There's no fixed timeline. Some volcanoes sleep for a few decades, others for thousands of years. The time scale can be almost unfathomable compared to a human lifetime, which is why people sometimes mistake dormancy for safety. We can listen to signs even when everything looks quiet. Scientists monitor dormant volcanoes with instruments that pick up what our senses can't. Tiny earthquakes that hint at magma moving, subtle bulges in the landscape that suggest the ground is filling like a balloon, and changes in gas composition that indicate fresh magma is releasing its internal steam and carbon dioxide. It's like checking a sleeping person's breathing and pulse. The mountain never truly goes off our radar. There's something deeply human about this relationship. We live with uncertainties in relationships, health, work, and we make choices about how to balance risk and reward. Building a home near a dormant volcano is a real-world expression of that balance. The soil is rich, the views are beautiful, but the possibility of future unrest always exists. People adapt. Evacuation plans, early warning systems, and community drills become part of daily life, a practical acknowledgement of the mountain's patience. And yet, even with all our instruments and plans, there's a humility in waiting. Scientists can detect many precursors, but they can't predict the exact moment of awakening. Nature has its own timing. Watching a dormant volcano is an exercise in patience, observation, and respect, traits that feel almost old-fashioned in our fast-moving world. So the next time you pass a forested slope that looks as peaceful as any park, remember that stillness can hide a slow, simmering power. Dormant means waiting, not gone. It's a reminder that beneath calm surfaces, forces work on scales we can barely imagine. How do we prepare, then, for what might return? In the next section, we'll look at the ways scientists and communities read those subtle signals and plan for a mountain's possible return to life. Volcanoes are the architects of islands. Think about that for a second. Whole stretches of land, entire nations, begin as molten rock and steam deep beneath the sea. That image, fire pushing through the dark, building itself into something that will one day host forests, farms, towns, is almost biblical, but it's also how the world actually gets made. Start with the Pacific. Walk with me in your mind to Hawaii. There's a different heartbeat there because those islands sit over a hot spot, a stationary plume of magma rising through the moving Pacific plate. Each island is a moment in time. Big Island is active, spewing new landscapes. Maui and Oahu are older, their sharp lava flows softened by rain and the slow abrasion of surf. If you ever stand on a black lava flow, you can still feel that raw sculptor's hand, the surface cooled to glass, the air smelling faintly of sulfur and ocean. It's humbling and strangely comforting, like seeing how a wound heals into a scar that becomes part of a person's story. Cross the North Atlantic, and you get to Iceland. Here the land is born along the mid-Atlantic ridge. Imagine plates pulling apart, magma filling the gap, and the island lifting itself inch by inch out of the sea. Iceland's landscapes read like an atlas of volcanic processes. Shield volcanoes that lay down broad sheets of lava, explosive eruptions that hurl ash into the sky, and fissures that create black deserts and steaming geothermal fields. Yet, after the fury, Iceland is one of the calmest places you can find. A country of hot springs and placid fjords, sheep grazing on lava fields that look like ancient armor. Locals say the land remembers its birth. In stories, sagas, and music, they speak to the idea that a violent beginning doesn't dictate a violent life. Japan shows another pattern, the meeting and clashing of plates. Volcanic arcs here are the result of one plate sliding beneath another, melting and creating a chain of peaks that rise out of the sea. The islands that became Japan were stitched together over millions of years. Each volcanic summit is layered with eruptions, ash, and time, and each slope has a human story. Villages that pray at shrines on volcano-flanked hills. Fishermen who have learned to read the sea because it remembers the same tremors their grandparents did. What's amazing is how quickly life claims what was born of fire. Primary succession is slower on oceanside lava than on continental rock, but it happens. Lichens, mosses, and windborne seeds begin the patient work of turning basalt into soil. In volcanic islands, you can often trace an ecological timeline by looking at the coastline. Barren black rock nearest to recent flows, then a ribbon of pioneering plants, then forests thick enough to hold endemic birds that exist nowhere else on Earth. That sense of being part of a timeline, seeing how ash beds and lava flows are the geological pages on which life writes new chapters, is what makes islands so intimate to the people who live on them. We should also be honest about the costs. Islands born in fire remain geologically young and therefore precarious. Eruptions, earthquakes, and tsunamis are part of the package. But island communities adapt in ways that are instructive. They build with the land's rhythms in mind, develop crops suited to mineral-rich soils, and cultivate cultural practices that honor both the threat and the bounty of their environment. Think of the winding lava rock walls in the Azores, the terraced taro fields of Hawaii, or the mountain shrines of Japan. Each is human response to a landscape still remembering its violent origin. So when you picture an island, the calm bay, the coconut palms, the sleepy village tucked between green slopes and a shimmering horizon, remember that it was once an incandescent thought of the planet, erupting into existence. That contrast between fiery birth and serene present is one of nature's great ironies, and it's also one of its most beautiful lessons. Destruction and creation are inseparable, and from heat and chaos, places of surprising peace can grow. As we continue, we'll explore how those island forms shaped not just ecosystems, but the cultures and lives that make them home. Look at lava long enough, and it stops being just molten rock. It becomes a kind of slow-motion thermometer. The colors tell a story you can read even from a distance. When lava is bright yellow, it's screaming hot, well over 1,000 degrees. That blast of yellow is raw thermal energy so intense it pushes the material into a nearly white-hot glow. You don't need to be a scientist to sense the difference. Yellow lava feels like the oven turned up past anything you'd use at home. As that same river of molten rock moves away from its source, the color shifts. bright yellow gives way to orange. That orange is still incredibly hot, still hundreds of degrees hotter than anything we normally handle, but it's losing energy. Imagine taking a pan off the stove. The pan starts bright, then slowly dims to a duller orange, then to a faint red. Lava behaves the same way, only on a grander scale. Watching orange melt into red is like watching energy slowly let go of its hold on matter. Red lava is cooler still. It's the visible sign that the heat is retreating, that the rock is beginning a one-way trip towards solidity. In the red stretches, you can often see the texture change. The flow thickens, crusts begin to form, and the surface tension that once let the lava move like liquid now starts to solidify into shapes. It's a reminder that temperature governs behavior. Hotter equals more fluid. Cooler equals more structure. If you've ever poked a dying campfire and watched the embers go from glaring red to dull black chunks, you already know this story. The glow of lava follows the same arc, just louder and with much higher stakes. That march from yellow to orange to red is literally temperature losing its light, one shade at a time. There's something almost human about it, like watching an exhausted athlete slow down after a sprint. You can almost feel the energy ebb. Eventually, the glow vanishes, and the lava turns black. That black isn't just darkness, it's a new kind of material. Rapidly cooled lava often forms a glassy surface. Obsidian, smooth, shiny, and starkly black. Where the moving interior once glowed, now there's a brittle skin that will break into sharp, glass-like shards. That skin tells you the lava's race against cooling has been lost. Heat has fled, atoms stopped dancing, and the story of the flow moves on as rock. I remember the first time I saw footage of a pahoeho flow up close. At first, it was this hypnotic yellow seam, then a strip of orange, then a band of dull red slipping beneath a fragile black crust. Even on a screen, I felt like I was watching an enormous hand paint the earth with a brush that gradually ran out of light. That feeling of witnessing energy transform into structure is why the colors matter. They're not decoration, they're information. There are practical reasons to read those colors too. For volcanologists and anyone observing from a safe distance, color helps estimate activity. A sudden return to bright yellow near a vent signals fresh, hot magma making its way to the surface. A field of cooling black crust tells you the flow has slowed or stopped. For the rest of us, the colors are a visceral cue. They remind us how small we are next to these temperatures, how quickly molten rock can go from something that glows to something that will cut your boot. Before you ever think about getting close, remember, the glow you see is a warning. It looks inviting in photos, molten rivers, molten fountains, but that light means hundreds to thousands of degrees of heat. Appreciate it from a distance, in person only with trained guides and safety measures, or in footage that captures the spectacle without putting anyone at risk. The color change also explains why volcanic glass exists and why it's so striking. When lava loses its glow and turns black, the cooling can be so quick that crystals don't have time to form, leaving behind that smooth, glassy texture. It's like freezing a moment of motion into a solid snapshot. So next time you see lava, whether on screen or in a safe viewing area, try reading the hues. Yellow is the peak of the action. Orange is the slow surrender. Red is the last stubborn heat. And black is the final form. Watching it flow is literally watching temperature give up its light, one shade at a time. A visual score of physics playing out in real time. When the plume finally settles and the black sky clears, the world looks like it's been wiped clean. Trees are stripped of leaves, roofs are gray with dust, and everything smells like metal and ash. It's easy to think the only story here is loss. But stay with me a moment, because that gray dust is also the first sentence of a very different story. One of renewal. Volcanic ash isn't just blasted rock. It's packed with minerals, bits of silica, iron, calcium, potassium, and tiny shards of volcanic glass, all ground so fine they can hitch a ride on wind currents across continents. At first, that dust is abrasive and sterile. It scratches skin, clogs engines, and makes the air taste harsh. Yet when rain begins to fall and sunlight returns, something quiet and profound starts to happen. Water softens the ash, dissolving minerals. Microbes and pioneering plants move in, slowly building organic matter. Over months and years, the ash weathers, binds with decaying roots and leaves, and becomes soil you can plant in. This is how some of the world's richest farmlands were born. Think of Java. The island's dramatic green terraces and patchwork fields owe a huge debt to centuries of eruptions. The same goes for Campania, the fertile plain around Naples, shaped in part by Vesuvius. Mount Etna in Sicily feeds orchards and vineyards with ground that keeps giving. When you taste a tomato from those slopes, or sip a wine raised on volcanic tuff, you're tasting the slow chemistry of rocks turned into food. The science behind that change is elegant in its own way. Fresh ash is high in reactive minerals and volcanic glass. These weather into clays and other minerals that hold water and nutrients. Certain soils that form from volcanic material, scientists call them andisols, have a remarkable ability to retain phosphorus and water while releasing essential nutrients slowly. That balance makes them incredibly productive for crops, from rice and coffee to grapes and vegetables. In practical terms, land that once looked devastated can, in a generation or two, support dense, thriving agriculture. I remember visiting a small farm on the flank of a volcano. The air still smelled faintly of sulfur, and the farmer led me by hand through rows of cabbages. He told me how his grandparents learned to plant immediately after a particular eruption, spreading compost over fresh ash and planting fast-growing cover crops. "We don't fear the dust forever," he said, wiping his hands on his pants. "We know the earth will change." That combination of patience and local knowledge is common where people live alongside volcanoes. They have learned to read seasons of destruction and decide when to sow, when to add organic matter, when to let the land rest. There's also a poetic side to this transformation that's easy to relate to. Think about times in your life when something fell apart: a job, a relationship, a plan. At first it's messy and sharp, and you can't imagine a way forward. But give it time. Let new things come in. Allow small habits and new people to settle, and something fertile can emerge. That's what volcanic ash does for landscapes. It creates conditions that invite renewal. Rain brings nutrients into reach. Sunlight feeds green shoots. Organisms, invisible at first, begin to turn mineral into life. Of course, this isn't a romanticized, instant fix. The first rains after an eruption can wash ash into waterways, causing problems for communities and ecosystems. Fresh ash can be toxic in the short term and poses real hazards, but the long arc is clear. What arrives as destruction can, with time and the right conditions, become one of nature's strongest builders. Farmers across the globe have learned to harness that process, and entire food cultures exist because of it. So when you next see a landscape dusted gray after an eruption, or when you face something that seems ruined in your own life, try to see the layers beneath. Under that gray is the raw material for growth, a mineral wealth that, with moisture, warmth, and patience, will knit itself into new soil. The world's richest fields didn't spring from nowhere. They were forged by fire and time. Creation often hides inside what first feels like ruin, and sometimes what looks like an ending is simply the beginning of the next harvest. Look out over the Pacific, and you're looking at Earth's restless seam, more than 450 volcanoes stitched in a vast horseshoe we call the Ring of Fire. It sounds dramatic, because it is. Tectonic plates, grinding, diving, and colliding along that rim force molten rock up through the crust, shaping everything from islands to mountain chains. It's the planet's most volatile boundary, and also one of its most creative. When you imagine a volcano, you probably picture an explosive eruption, clouds of ash and lightning. That's part of the story. But living near the Ring of Fire taught me how much more complicated and personal it is. I've stood on the black sand of an island that was born in a single violent event decades earlier, and I've chatted with rice farmers whose terraces thrive because of volcanic soil. The same processes that can level a town also create lush lands and new coastlines. So how does this enormous horseshoe work? Most of the activity comes from subduction zones, places where one tectonic plate slips beneath another. Imagine a conveyor belt. The oceanic plate dives down, melts a bit as it sinks, and that molten material rises. Over millions of years, that repeated upwelling builds volcanoes, one after another, like beads on a string. The Pacific's western rim, Japan, the Philippines, Indonesia, and the eastern rim, Alaska, the Cascades, the Andes, are all parts of this chain reaction. Names like Mount Fuji, Krakatoa, Mauna Loa, Mount St. Helens, and the volcanoes of Kamchatka aren't just tourist postcards. They're landmarks of ongoing geological negotiation. Krakatoa's 1883 eruption reshaped coastlines and sky patterns worldwide. Mount St. Helens' 1980 blast changed how scientists monitor volcanoes and how communities plan for the worst. And places like Anak Krakatau, literally the child of Krakatoa, remind us that volcanoes don't just destroy, they can create entirely new land. Living with this reality means people have adapted culturally and practically. In Japan, you'll find centuries-old mountaintop shrines and festivals honoring the spirits of volcanoes, traditions that blend respect, fear, and gratitude. In Indonesia and the Philippines, farmers know exactly which slopes will give the richest harvests after an eruption. And modern towns have evacuation routes, sirens, and community drills, small human systems trying to keep pace with deep time. There's also a quieter, less obvious bounty. Volcanic regions are mineral-rich: copper, gold, geothermal reservoirs. Countries on the Ring of Fire tap that heat directly. Geothermal plants in places like the Philippines and parts of Indonesia supply clean energy to millions. Think of it as turning risk into resilience, harnessing the heat beneath our feet rather than only fearing it. Science has become a frontline partner in these communities. Networks of seismographs, gas sensors, satellite radar, and local observers watch for changes in ground swell, gas emissions, and tiny earthquakes. Early warnings don't make eruptions invisible, but they save lives. I remember standing with a volcanologist watching live tremor charts, simple spikes and dips that translated into immediate, consequential decisions for towns down the slope. Those instruments are the modern lifelines across the Ring of Fire. And yet, for all the monitoring, human stories remain at the center. There are parents who have rehearsed one backpack with essentials for an emergency. There are grandparents who tell the stories of past eruptions like family legends, warnings wrapped in memory. That tension between awe and anxiety, between destruction and creation, is what makes the Ring of Fire feel less like a distant geological fact and more like a daily reality for millions. As we move from the fiery edges of the Pacific to how those eruptions ripple across oceans and cultures, keep in mind this paradox. Fire that can take away can also give back, shaping landscapes, livelihoods, and the very history of the people who live along its curve. And beneath all that, the planet is breathing. Volcanoes give the Earth a voice, deep rumbles, low frequencies that don't so much travel through the air as ride through stone and soil. You won't always hear them in the register of conversation, but you can feel them. A subtle pulse under your feet, windows that tremble, a dog that lifts its head from the rug. It's the same kind of bass you feel at a concert when the speakers push air. Only the stage is the whole crust, and the amplifier is molten rock moving miles below. I remember standing once on the shoulder of a quiet volcano just after dusk. The sky had turned the color of old coins, and a hush folded around the trees. Then, a low, steady rumble threaded through the ground. At first, I thought a train was passing far away. Then I realized there was no track, no engine. The sound wasn't in my ears, it was in my chest. My heartbeat slowed to match it for a moment, as if the mountain's pulse had reached mine. A nearby shepherd's dog got up and walked to the ridge, sensing something I couldn't completely name. That moment made me think of the planet as alive in a way that textbooks rarely capture. Geologists call many of these signals infrasound when they are below 20 Hz, and volcanic tremor when the motion is continuous. These are not one-off bangs or explosive blasts. They are sustained, low-frequency sighs and groans. Low frequencies travel far because they lose less energy to scattering and absorption. That means a deep rumble from a volcano can be recorded hundreds of kilometers away, translating to a kind of long-distance conversation between Earth and instruments we set into the ground. Because these frequencies sit below the conscious hearing range, scientists often speed up or shift the recordings to bring them into a register we can process. When you hear the sped-up version, the rumble becomes a haunting chord, and you suddenly notice the structure, pulses, harmonics, and patterns that would otherwise be invisible. Listening to those translated sounds, you can hear the difference between a volcano breathing calmly and one that's building pressure. It's like being able to tell if someone is asleep, awake, or restless just by listening to their breath. But even without instruments, our bodies are sensitive in surprising ways. I find that in old houses built on bedrock, you'll feel the earth breathe in creaks and shivers through the floorboards during windy nights. In urban settings, the rumble mixes with traffic and machinery, masking its source. But sometimes buildings will sing in unexpected frequencies, and you realize the ground itself is humming underneath the noise. Children notice these things more readily, how their toys tremble, or how their tooth rattles when the world gives a low, distant sigh. There's an intimacy to it. The planet is not distant. It's underneath you, a steady presence. For communities near volcanoes, that hidden voice becomes part of daily life. People learn to read the mountain's moods the way sailors learn the sea. They notice changes in pitch and length of rumbles, the way a tremor lingers rather than ends abruptly. Local knowledge combined with seismometer data gives a fuller picture. Machines tell frequency and amplitude, while people provide context. An unusually long groan at dawn, birds deciding to leave the trees early, warm gusts scented with sulfur. In my conversations with residents, I was struck by how personal these descriptions are. The mountain as an old neighbor, grumpy in winter, silent in summer, and talkative before it shifts. There's also a metaphorical comfort in imagining earth breathing. When you place your palm on warm rock or sit against a cool boulder, you're touching something that has been moving in cycles longer than any human life. Those cycles register in micro vibrations and low-frequency waves. If you close your eyes and focus, you can match your breathing to that slow rhythm, and the scale of time expands. Problems shrink for a moment. That doesn't lessen danger where it exists, but it adds perspective, a reminder that we're part of a system where deep, slow processes shape the landscape we walk every day. As we learn to listen better with instruments and attention, the voice of the planet becomes less mysterious and more urgent. The same low-frequency signals that are poetic also carry information about magma movement, gas escape, and structural changes underground. Translating those whispers into warnings is a modern form of listening, pairing ancient sensory intuition with precise measurements. So next time you stand on a hillside or lie awake in a mountain town and feel the floor tremble, think of it as the Earth's breath passing through you. It's both a scientific signal and a human story, a low, steady heartbeat reminding us we're standing on something alive. Scientists and artists both turn those inaudible lows into something we can intuitively understand. Seismometers, infrasound arrays, and simple geophones convert ground motion into electrical traces. Engineers then shift or speed recordings so our ears can follow the pattern. Musicians have sampled those altered tracks, folding volcanic tremor into compositions that feel ancient and immediate at once. I remember downloading a sped-up recording from a research site and playing it through headphones late at night. That low chord moved like a tide, and for a moment the map in my mind rearranged to place the mountain front and center of the room. You don't need fancy gear to begin listening. Press the heel of your hand to a tree trunk, or put a palm flat on an old stone wall during a cool morning, and pay attention to the faint vibrations. Even a smartphone app that measures acceleration can show spikes and rhythms where your ears perceive nothing. Listen at dawn or late at night, and let that low, slow pulse remind you that landscapes are alive, not as a threat, but as a deep-time companion. When we listen, we also learn to care, and we act now. You can almost feel it before you see it. A pressure in the air, the earth humming under your feet, and then a darkness rolling up from the crater like someone pulling a blanket over the sky. But this is not just darkness. From the heart of that ash cloud, jagged veins of light stab outward, lightning that doesn't come from rain or a thunderhead, but from hot rock and grit thrown into the air. Volcanic lightning is one of those moments where the planet reminds you it's alive, loud and beautiful in the way storms and fire can be at once. Imagine standing at a safe distance, hands wrapped around a coffee that's gone lukewarm because you forgot to sip it. The volcano exhales, ash, gas, fragments of lava, and those tiny particles start to rub against each other. It's like walking across a carpet and touching a doorknob. Friction breeds electricity. Scientists call this triboelectric charging. In an eruption, it's amplified. Billions of particles colliding, fracturing, and exchanging electrons in a crowded, boiling atmosphere. The result is a growing electrical charge separated into regions inside the plume. Positive pockets here, negative pockets there, until nature finds a way to balance it with a sudden, violent discharge. Lightning. Visually, volcanic lightning is surreal. Regular thunderstorms often produce lightning that tracks through open air, flinging across the sky. Volcanic lightning, by contrast, often lights the ash cloud from within. You'll see a glow that seems to come from the belly of the billowing plume, then a bright white or bluish streak tearing through, cracking the shadow into momentary pieces. Because the source is ash and gas, the light can be strangely diffuse or wildly elemental, sometimes a single thick bolt, sometimes a spider web of thin veins, sometimes a cascade of branching flashes that look like a living sculpture. It's as if the volcano is painting in electricity. There's another layer to the story: temperature and moisture. In very powerful eruptions, the plume reaches high enough that ice can form on the suspended particles. Once you've got ice crystals mixing with volcanic debris, you've got the same ingredients that make thundercloud lightning. That's why some volcanic plumes behave electrically like convective storms, with frequent, powerful discharges. But in many cases, the lightning comes primarily from particle collisions, dry, abrasive, and intense. Either way, the sensation is the same: a storm born of heat and dust, a fleeting fusion of heaven and earth. This phenomenon has a strangely personal quality. Think about times you've seen a fireworks show, when each burst throws up a perfect, impossible bloom of light, and you feel small in the best possible way. Volcanic lightning taps into that same mix of fear and wonder. People who've watched archival footage often describe a jolting combination of awe and unease, that the ground underfoot is reaching up to meet the sky. Photographers and storm chasers chase that feeling. Long exposure cameras capture arcs and sheets of light that the human eye might miss, and slow-motion footage strips the flash down into a sequence that looks almost choreographed, every strike different and beautiful in its own terrifying way. There's also a human story in the science. For volcanologists, lightning is neither just a spectacle nor an inconvenience. It's a diagnostic tool. The timing and frequency of electrical discharges can reveal details about the plume that are otherwise hidden. A sudden burst of lightning early in an eruption may indicate intense fragmentation of magma, more particles being created, more collisions, more charge separation. Instrument packages mounted on drones and ground stations measure electromagnetic signals, helping researchers estimate particle sizes, plume height, and even eruption vigor when visibility is poor. In that sense, every flash is a data point, and every crack of electricity tells a small part of the volcano's tale. Safety is essential to mention without sounding alarmist. The lightning itself can extend beyond the ash column into the surrounding air and even to the ground. Aircraft are also at risk. Ash can damage engines and electronic systems, while lightning adds another unpredictable element. So while it's tempting to get closer, to feel the heat and smell the sulfur, professionals maintain strict exclusion zones. Respecting those boundaries keeps curiosity from becoming tragedy. But let's bring it back to the sensory. Picture a night scene, a low orange glow from the vent, then a sudden, calamitous whiteness that makes you blink. The ash cloud, usually a black silhouette, fills with veins of pale blue like frost on a window pane. You can hear it too, not just the thunder from collapsing lava columns, but a sharp snap when a bolt breaches the plume. Afterward, there's a hush, then the steady sound of ash settling, the world a little quieter, as if the sky has exhaled. For those producing a video, volcanic lightning offers cinematic opportunities that practically write themselves. Use slow-motion clips to reveal branching patterns. Cut to close-up footage of falling ash to show why particles charge. And overlay electromagnetic data visually to tie the spectacle to the science. Personal testimonials. A volcanologist describing the first time they heard a plume sing with electricity, or a pilot recalling the eerie flash at cruising altitude. Add human texture. Keep the pacing deliberate. Let the viewer savor both the visual drama and the explanation behind it. Finally, there's a poetic side we shouldn't shy away from. Lightning over a volcano is more than an atmospheric oddity. It's a reminder of connection. Heat that comes from deep within the earth meets the air above. The hard rock becomes dust and then light. For a few seconds, the planet's internal processes become a visible conversation between ground and sky. That fleeting fusion, violent, brilliant, utterly alive, is why people risk cold, long hours and uncomfortable positions to watch. It's a story told in flashes, unpredictable, dangerous, and impossibly beautiful. Transition to the next section. Explore how scientists replicate and measure volcanic charging in the lab and what that tells us about eruption forecasting. Now imagine fire trying to move through a frozen world. In Iceland and a few other places, that's not a metaphor. It's literal. Volcanoes erupt underneath glaciers, and the moment red-hot magma meets ancient blue ice, something dramatic happens. The ice screams, steam billows, and the landscape is rewritten in hours. Close your eyes and picture standing on a ridge with the wind cutting at your face. Below you, a column of steam shoots up, white as a church steeple against a pale sky. It's not fog. It's volcanic heat meeting kilometers of ice. The first thing you notice is the sound. A distant, hollow roar, followed by a higher, cracking chorus, as ice fractures and meltwater rushes. If you've ever boiled a kettle in winter and felt the sudden rush of steam, multiply that experience by 1,000,000. The steam towers are like nature's pressure valves, letting off what can be an enormous buildup of energy. The science that makes this spectacle so striking is surprisingly straightforward. Magma under a glacier cools almost instantly when it meets meltwater. That rapid cooling shatters the lava into glassy fragments, a rock called hyaloclastite, and produces violent steam-driven explosions known as phreatomagmatic eruptions. Because the eruption happens under ice, the debris is trapped and often deposited in odd bulbous shapes. Over time, If lava keeps rising and the ice is thick enough, it can build a flat-topped, steep-sided volcano called a tuya, a volcanic table mountain that looks like the result of a sculptor carving a cake with a hot knife. But the visual drama is only the beginning. The meltwater created in these events doesn't always drip quietly away. Sometimes it's stored under the glacier until, suddenly, a dam gives, and a Jökulhlaup, an Icelandic glacial outburst flood, surges out. These floods are not slow spreads. They're powerful, sediment-laden rivers that can roar down valleys, rip up roads, and change the map in one night. For the people who live there, that's tangible. Farms that were safe a week ago become islands in a braided soup of sand and stones. Riverbeds are rearranged, and bridges have to be rebuilt. Icelanders have stories passed down about nights when the sky lit up and the ground shook. Modern scientists and emergency services translate those stories into monitored seismic patterns and evacuation protocols. When Eyjafjallajökull erupted in 2010, the subglacial nature of the eruption produced huge ash clouds and meltwater floods. The ash then traveled across Europe, grounding flights and reminding everyone how interconnected these feats of nature can be. It's a stark human reminder. What happens when fire and ice meet doesn't stay local. Being near one of these events is an oddly intimate experience. You smell the mineral tang of sulfur and wet stone, see ash dusting the snow like powdered sugar, and feel steam on your face that somehow seems both hot and cold. There's a constant negotiation between awe and caution. Photographers creep closer to capture the steam towers. Geologists set up sensors that listen to the subtle changes in the earth. Farmers keep an eye on river levels. That human element, curiosity mixed with practical survival, makes the scene relatable. We all want to witness something magnificent, but we also want to come home. And the long-term result is beautiful. New valleys carved where ice once lay, fresh plains of sand and rock spread like a painter's wash, and new mountains born from the crucible of heat and cold. The landscape left behind is raw and honest, scoured by water, sculpted by explosions, and waiting for life to reclaim it. Mosses and lichens arrive first, then grasses, and over centuries, entire ecosystems adapt to ground that was literally remade in a single event. So when you think of volcanoes, don't only picture lava flowing over black rock. Think of the opposite. Fire trying to move through ice, steam towers bleeding into a cold sky, and whole valleys born from a momentary meeting of extremes. It's nature at once violent and creative, and it's a reminder that our planet keeps changing in ways that are as dramatic as they are beautiful. Not every volcano keeps a ledger of future eruptions. Some simply run out of steam. Their molten hearts cool, the plumbing seals, and what was once a fierce engine of change becomes, over millions of years, a quiet hill or a ragged spire. Those are the extinct volcanoes, not threats, but monuments. They're the Earth's way of turning fire into memory. Picture hiking up a rounded peak that, from a distance, looks like any other mountain. You step on broken basalt, run your hand over glassy obsidian edges that now feel warm from the sun. And it's almost impossible to imagine that this same rock once flowed like a river of light. For me, that cognitive flip is the magic. Standing on something that was once utterly alive and feeling the calm of it now. It makes human time feel both tiny and tender. Our lifetimes are brief flickers compared with the cooling of a magma chamber, but we can still walk where that fire once moved. So what happens when a volcano goes extinct? The story is simple and patient. Deep beneath, a magma chamber, a reservoir of molten rock, gradually loses heat. The magma crystallizes and hardens. Conduits that once fed eruptions fill with solid rock. Above, rain and wind and glaciers do their slow work, wearing away the softer layers and revealing the stony skeleton. Sometimes the most dramatic parts remain. A volcanic plug that resisted erosion becomes an isolated tower, or a ring-shaped caldera collapses and fills with water to form a lake. We get a new landform that tells a long story in plain stone. Those forms are everywhere. Look around and you'll spot the evidence. A circular basin ringed by cliffs, a lonely butte rising out of a plain, or sweeping plateaus of basalt that once poured from fissures. Famous sites: the columnar basalt at the Giant's Causeway, the serrated necks and spires like shiprock in the American Southwest, the grassy dome of Arthur's Seat in Edinburgh, are all chapters from the same book. Their accessible history. You don't need to read a paper to feel the narrative. You can sit on the rock and feel the weight of age under your butt. There's an intimacy to extinct volcanoes that I think people respond to. Active volcanoes inspire awe and a kind of respectful fear. They are alive and unpredictable. Extinct volcanoes invite curiosity and reflection. Families picnic on their slopes. Hikers bring dogs and cameras. Artists paint their profiles at sunset. I've seen couples pick a sheltered ledge on an old lava flow and sit in silence, as if the quiet of the stone offers permission to slow down. There's a comfort in their permanence. They've outlived storms and empires, and they'll outlast us too. They also shape lives in practical ways. Soils weathered from volcanic rock can be startlingly fertile. Vineyards, orchards, and farms often favor these slopes. The rocks themselves become resources, quarries, building stones, and cultural symbols. Entire cities sometimes grow around these features, their skylines borrowed from ancient eruptions. In folklore and myth, extinct volcanoes become characters, sleeping giants, thresholds to the underworld, markers of divine wrath. Those stories are another way communities make sense of the deep time written in stone. If you're ever traveling, I encourage a simple experiment. Find an old volcanic plug or caldera and climb it. Bring no textbooks, just a willingness to listen to the landscape. Touch the rock. Notice the layers, the joints, the places where water has carved tiny canyons. Think about the contrast between the fierce chemistry that formed it and the slow, patient weathering that carved it into its present shape. Let that contrast change the pace of your thoughts for a few minutes. It's humbling and oddly consoling. Extinct volcanoes are monuments, not because they're grand or famous, but because they hold time in a way nothing else does. They show us cycles, heat to cold, motion to stillness, chaos to order, and they let us stand, literally, on the result. They remind us that the earth keeps records you can touch, and that some stories need millions of years to read. Now, as we move on, we'll look at how those cooled giants sometimes get rewritten by other forces. The same weather and life that erode them also paint them with new meaning. Step closer, and you can feel it. A shimmering curtain of steam, the air tasting faintly of sulfur, the ground humming with stored energy. places that look like the last stop on Earth. Boiling pools, fumaroles, ribboned lava fields are actually some of the planet's busiest intersections of life. It's easy to picture these sites as empty, brutal landscapes, but look more closely and you'll see color, movement, and strategies so clever they almost feel like a different language. Start with the hot springs and geysers. Pools that flirt with boiling aren't sterile. They're layered with microbial life. Cyanobacteria and other thermophilic microbes form brilliant mats of orange, green, and brown, like abstract paintings stretched over steaming water. These organisms have evolved proteins and membranes that refuse to denature in heat. Their enzymes curl into shapes that stay useful where ours would melt away. Some of those enzymes, like the famous TOC polymerase from Thermus aquaticus, found in Yellowstone, changed human history by making PCR possible, the very tool that revolutionized modern biology. That fact is a little humbling. Something thriving in boiling water helped us look at life on a molecular level. Walk along a geothermal edge, and you feel tiny worlds stacked on top of each other. Near the hottest centers, archaea, ancient, oddball microbes, often dominate. They stabilize DNA with special proteins. Their cell membranes use lipids shaped to resist high temperatures. A few meters away, where the water cools even slightly, cyanobacteria take over, capturing sunlight and building the first crumbs of an ecological cake. The colors shift with temperature and chemistry, so a single pool can be a natural thermometer you can read with your eyes. Go deeper, literally, to the abyssal plains where tectonic plates pull apart and superheated water gushes from black smokers, and the story twists into something stranger. There, sunlight is absent, so life doesn't rely on photosynthesis. Instead, chemosynthetic bacteria convert chemicals like hydrogen sulfide into organic matter, forming the base of entire ecosystems. Giant tube worms cluster around vents, a riot of red plumes that are actually packed with blood rich in sulfur-carrying molecules. They have no mouth. They house bacteria that feed them from the inside out. Nearby, crabs, clams, and shrimp graze or guard territories, all linked to chemistry rather than light. Those deep-sea communities are a reminder that habitable is not a single box. Life finds alternative currencies, chemical energy, heat gradients, mineral-rich plumes, and builds from there. It's not chaos, it's a different kind of orchestra, with each species tuned to extremes we'd consider hostile. Back on land, the aftermath of an eruption tells another part of the same story. New lava is essentially rock spelled out in fire, sterile, jagged, and nutrient-poor at first. Yet, within years and decades, cracks and cooled flows become hosts. Lichens and mosses are the first colonizers, clinging to glassy surfaces, secreting acids that begin to break rock into soil. Seeds carried on wind and bird are like tiny immigrants landing in a strange new country. If conditions allow, grasses and pioneer shrubs take hold. In places like Hawaii, the ohia lehua is legendary for showing up early on fresh basalt, its roots prying into cracks and slowly knitting organic matter into the lifeless stone. Over time, a mosaic of stages creates soil, retains water, and invites insects, birds, and eventually more complex plant communities. What I find most striking is how these processes turn catastrophe into opportunity. An eruption can wipe out a forest, flatten a valley, rain ash over villages, but the same heat and minerals that raise life also release nutrients and create niche habitats. Nature doesn't rush in as some perfect healer. It experiments, fails, repeats, and eventually finds a new balance. That rhythm, destruction followed by renewal, harshness matched with adaptation, feels deeply human. We rebuild after our own disasters, repurpose what's left, and learn to live with change. So when you next see steam rising from a spring or a map dotted with volcanoes, remember, these are not wastelands. They are laboratories of resilience, testing life at its limits, and, in the process, teaching us how flexible and inventive biology can be. The creatures of heat don't just survive, they reframe what it means to be alive. But not all volcanoes announce themselves with dramatic cones and flowing lava. Many of them are secret keepers, vast, slow burners tucked beneath fields, forests, even cities and lakes. You could be standing on top of one and never know, plucking dandelions from a lawn that, on a geological scale, is sitting above a simmering, centuries-old furnace. Take Yellowstone. From a distance, it looks like any other national park. Hot springs, forests, wide valleys. Up close, you see the odd things. Pools that steam in cold air, geysers that erupt on a schedule, terraces of white minerals etched into the ground. Those are the face of something much bigger below, a massive caldera, the scar left by ancient gigantic eruptions. The caldera doesn't roar every day. Instead, it breathes. The ground rises and falls a few centimeters at a time. Hot water cycles through fractures, gases seep up. It's slow, but it's not dead. That slow breathing has been shaping the landscape for hundreds of thousands of years, nudging rivers, altering vegetation, and making the place as dramatic as it is fragile. That kind of hidden volcanism is easy to romanticize, but it's also strangely intimate. Imagine a farmer in the Midwest cultivating corn on flat land that used to be molten rock millions of years ago. Or picture a small town built on the rim of a quiet lake, unaware that the water sits inside a caldera formed by a prehistoric eruption. The ground there can feel normal underfoot. The same gravel road, the same playground, but the heat and chemistry a few meters below are different. Warm springs, sulfur smells, mineral stains on rocks, little plumes of steam when winter comes. To live in those places is to live with deep time, pressing down gently on everyday life. You probably know the obvious signs of an active volcano, ash clouds and lava, but the hidden ones leave quieter clues. Hot springs and geysers are the postcards. Ground that bulges a few inches over months says there's pressure shifting underground. Tiny earthquakes, barely felt, are the Earth's whispers. Changes in gas composition, spikes in carbon dioxide or sulfur dioxide, are like a breath that tells scientists something is happening below. Satellite images can show the landscape tilting ever so slightly. Taken together, these subtle signals let researchers read the story beneath our feet before things become truly hazardous. Sometimes those signals are ancient echoes. Calderas are created when an enormous eruption empties a magma chamber and the ground collapses into the void. After that dramatic event, a new chapter begins. A vast, hidden reservoir cools, water circulates, minerals accumulate, ecosystems adapt. Over tens or hundreds of thousands of years, the memory of the eruption fades from human history, but the landscape keeps the scars. Lakes form where the caldera basin collects water. Hot springs dot the shorelines. Vegetation changes because of the soil chemistry. People settle. Farms are laid out. Towns thrive. All above a sleeping system that may or may not wake on a time scale we recognize. There are places, though, where humans and hidden volcanic systems collide in a much more immediate way. Around Naples, the Campi Flegrei caldera underlies suburbs and ancient ruins. It has a history of uplift and unrest that scientists monitor closely. In Indonesia, Lake Toba is a reminder that some of the world's largest volcanic events leave behind water-filled basins that look ordinary until you learn their origin stories. Those examples make the point plain. Hidden volcanoes are not a purely academic curiosity. They shape real lives, real cities, and real decisions, from where to build to how to prepare for rare but potentially large events. For me, there's nothing abstract about it. Walking across a boardwalk over a steaming spring, I remember the hiss of hot water at the edges and the sharp mineral tang on the air. It makes you aware that what looks serene now has a history of violent transformations, and that the ground beneath your feet is not immutable. That tension between calm surface and restless depth is part of what makes these places so compelling. Scientists have gotten better at reading the signs, using networks of seismometers, GPS stations, gas monitors, and satellites to keep an eye on these quiet giants. That doesn't mean every bulge or bubble will lead to disaster. Often the Earth simply adjusts and settles. But it does mean we can be informed and prepared. Living above a hidden volcano is living with a story that stretches far beyond human memory. A slow, powerful narrative that we can observe, respect, and learn from. At first, the silence is not empty. It's thick and deliberate, a sound that settles into your bones. In those first hours after the violence of the eruption, you notice the small things. A twig hitting the ground without being heard. The distant clack of cooling rock that sounds too soft to be real. Ash falls like slow gray snow, coating everything in a dull, weighty hush. If you stand still long enough, you can feel the world exhaling, as if the mountain itself is letting go. Camera lingers on a hand brushing ash off a windowsill. The gesture is both automatic and sacred. A way to make sense of the mess, and a way to touch the land that suddenly feels different. The air is still warm at first, carrying a metallic edge that makes your throat tickle. Over days, that edge softens. Steam that once boiled from fissures in the ground thins into wisps and finally fades to nothing. Where molten rock raced and roared, the lava now sits, cooling into a dark, glassy crust. Up close, it cracks and groans like an old ship's hull, tiny sounds that remind you this is not finished. It is simply changing shape. Time loosens its urgency. Days become measured by the fall of ash and the slow dimming of heat. The sun, at first dull behind a veil of fine gray, starts to clear in certain pockets. Patches of light find their way into the gray and reveal new textures. Blackened tree trunks, bent and scarred but standing. Rooftops under 100-layered dust. Streams studded with ash like tiny pebbles. You begin to notice the ways life had been pushed outward and is now looking back in. A fox appears at the edge of a burned field, ears twitching. A single robin flutters onto a chimney like a punctuation mark. Life is tentative, but present. Months will pass before the real healing shows itself. The first colonizers are not grand or showy. Lichens and mosses, tiny green and gray patches that anchor themselves to cooled lava and ash. They are the slow-working artists that lay down the first nutrients. Grasses follow, then hardy shrubs, each generation softening the landscape a bit more. Seeds ride in on the wind, hitchhiking on migrating birds, or arrive buried in the guts of animals looking for food. Rivers, clogged with sediment and ash at first, begin to carve new channels and clear their beds. The sound of water returning, that familiar living noise, is one of the most hopeful signs. It makes the air feel less like a cemetery and more like a place that can sing again. Watch closely, and you'll see surprising births, tiny shoots pushing through the ash like questions. Wildflowers bloom in odd places along cooled lava flows, their colors bright and insolent. Insects find niches. Pollinators follow. Birds that left months ago start to come back because there is food to be found, seeds to be pecked, insects to be caught. Over years, saplings become trees. The burned skeletons of forests are gradually softened by fresh green. It's not a return to what was. That would be impossible, but something new and steady and honest. The landscape holds the memory of the eruption in every ridge and scar. You can read the past in layers of ash, in the shiny seam of obsidian, in the blackened hollows where whole groves once stood. Those marks don't feel tragic forever. They become part of the place's identity. Standing on a ridge that overlooks a cooled flow, it's easy to imagine the heat, the fury, the smoke. But it's also easy to notice a different truth. That stillness can be restorative. There is a dignity in the way the land keeps its scars and still opens itself to sunlight. That duality, memory and peace, is what people feel too. Walking through new chutes, you might remember the fear, the night you watched the sky glow. But you also feel a quiet gratitude as small life returns under your feet. The act of rebuilding, of cleaning ash off an old photograph or letting a neighbor use your generator, folds human resilience into the landscape's recovery. Nature doesn't forget the eruption, it carries it like a story. Yet it moves on in its own steady tempo, finding balance again. So the picture left behind is not a reset to zero. It's an archive, permanent traces, fresh beginnings, and plenty of room for hope. In the quiet after the eruption, the world doesn't rush to forget. It remembers, and in remembering, it makes a place for new life to take root. That's a kind of peace that feels earned and deeply, quietly human. Quietly. Picture a volcano not as an isolated, dramatic event on Earth, but as a cosmic habit, a way planets and moons express their insides. We tend to imagine volcanism as something rooted in palm trees, lava flows, and tourists huddled on a safe ridge. But lift your imagination out of the atmosphere, and you find the same basic story playing out in wildly different costumes across the solar system. Take Olympus Mons on Mars. If you've ever stood at the rim of a terrestrial volcano, you know how small a person feels against that scale. On Mars, that feeling is multiplied until it becomes almost absurd. Olympus Mons is about 22 kilometers tall, roughly 3 times Mount Everest. and its base stretches about 600 kilometers across. It's a shield volcano built by slow, very fluid lava spreading out in vast sheets. Because Mars has lower gravity and a thin atmosphere, lava can travel farther and pile up into a gentler, broader mountain than anything we see on Earth. Try to imagine hiking up something that would swallow an entire state park, and you get a taste of how different but familiar planetary geology can be. The same molten rock, the same cooling and layering, just writ on a scale that makes our backyard volcanoes look like molehills. Then there's Io, one of Jupiter's innermost moons, which feels like a different element entirely. Instead of the slow, patient lava of Olympus Mons, Io is relentless and chaotic, the most volcanically active body in the solar system. That fury doesn't come from radioactive decay the way much of Earth's heat does. It's tidal heating. Jupiter's enormous gravity flexes Io like a rubber ball, squishing and stretching at every orbit. The result is internal friction, which becomes heat, which becomes volcanoes that spit sulfur and molten rock across the surface. Imagine standing on Io, if you could, and watching plumes hundreds of kilometers high, painting the sky with yellows, reds, and blackened smoke. The lava there can be hotter than most terrestrial lavas, and the surface is a patchwork of fresh flows and painted plains. It's messy, violent, and breathtakingly alive. And then, remember that volcano doesn't always mean hot rock. In the deep cold of the outer solar system, the same principle, internal pressure finding a vent, drives cryovolcanism, where water, ammonia, or methane substitute for molten rock. Enceladus, a moon of Saturn, shoots jets of icy particles and vapor through fissures at its south pole. Those geysers feed Saturn's E-ring and hint at a warm subsurface ocean. The image of water shooting into the black like a shaken soda bottle is strangely intimate. It evokes geysers back on Earth, but in a setting so alien, it makes you rethink what hot and active mean. What connects all these scenes is a simple truth. Where there's internal energy and a path to the surface, creation happens. Heat and pressure are stubborn. They will find a way up, even across millions of kilometers of vacuum. That universality is oddly comforting. It says the processes that gave us landscapes, soils, and possibly the chemical soup for life are not Earth-exclusive quirks, but fundamental outcomes of physics and chemistry. When I hike near a lava flow back home, or watch a documentary of Io's fire-scarred plains, I feel the same mixture of smallness and connection. We're witnessing the same creative impulse, whether it's sculpting Mars into a giant shield volcano, or carving fountains of ice into Saturn's rings. So when you think about volcanoes, don't just picture molten rock on a Hawaiian hillside. Think bigger. Planetary engines at work, shaping worlds, recycling materials, and sometimes even opening windows on hidden oceans. That idea that the universe makes room for creation in so many forms is a doorway. It invites the next question. If volcanism is one thread connecting worlds, what other forces weave planets into the diverse living systems we keep discovering? When the thunder of an eruption finally quiets, the world feels like it has exhaled. The sky, streaked with ash and smoke, slowly clears. The ground that was once a living, breathing forest or village is changed beyond recognition. If you've ever stood at the edge of a cooled lava flow, you know that strange mix of awe and hush, the loud, terrible music of the eruption replaced by a kind of solemn silence. That silence isn't empty. It's the first breath in a new rhythm. It helps me to remember that volcanoes are not only agents of loss, they are sculptors. The same heat that flattens trees and shreds roofs also forges rock and raises land. Islands are born this way, fire meeting ocean, then cooling into something that plants and people can call home. Ash, which at first feels like the residue of destruction, becomes a blanket of minerals. Those minerals, iron, potassium, phosphorus, are the nutrients that over time feed new growth. I think about how a blackened hillside, months after an eruption, starts to show specks of green, lichens, mosses, tiny grasses piercing the dark. It's a slow, quiet reclamation that feels almost intimate. This is where the twin nature of volcanoes feels personal. In my life, big endings have often been messy, loud, and terrifying. I remember losing a job and feeling like everything around me had been scorched. For a while, I couldn't imagine anything growing there again. But little by little, I found that the space left behind allowed me to learn different skills, meet different people, and eventually plant projects that were stronger and more nourishing than the old ones. The same could be said for communities that rebuild after eruptions. They carry loss with them, memorials, stories, scars, but they also inherit this strange, fertile gift from the molten earth. There's a rhythm to it: heat, collapse, cooling, renewal. It reminds me of the way seasons work, or the way we recover after any crisis. Pain is not erased, it's incorporated. Ash becomes soil. The earth does not pretend the fire never happened. Instead, it transforms the aftermath into a foundation for what comes next. That honesty, acknowledging harm while actively making room for growth, is something we can learn from. Walking over a plain of cooled basalt, you feel the history underfoot. The rock is evidence of what passed, and yet its surface holds promise. Seeds that land in cracks find microclimates where nutrients gather. In time, birds come, scattering more seeds. Fungi settle in and begin a slow dance of decomposition and renewal. It's a reminder that ecosystems are not linear. They evolve through disturbance and response, and that disturbance can be generative. We should also be honest about the cost. For people who lose homes or livelihoods, the period after an eruption is terrifying and uncertain. Recovery requires resources, time, and compassion from the broader community. But if we only focus on destruction, we miss the whole story. The story that also includes creative force and resilience. Embracing both truths helps us respond with care, not with denial, or with a rush to sanitize the narrative. When I stand in those quiet, cooling places, physically or in my memory, I feel a kind of humility. There's something humbling about watching a planet that's older and larger than any of our dramas reclaim itself. It's calming and, paradoxically, invigorating. The sight of the first green shoots after blackened earth tells you that life is persistent, that balance returns even if it looks different. That balance is not neat. It's textured, layered with loss and gain, grief and gratitude. So what does this mean for us practically? It means we can hold complexity without losing our center. We can mourn loss while we participate in healing. We can support rebuilding efforts that respect both the past and the future of a place. And on a personal level, we can allow endings to be endings, not as failure, but as an invitation to something new. That doesn't cheapen the pain. It honors it, because it recognizes that pain can include the seeds of growth. As the fires cool, calm returns, and with it, life. The earth breathes, and we breathe with it. That breath is a reminder that destruction and creation are not enemies but neighbors, often sharing the same space. If we learn to listen to that breath, to witness the silence after the roar, we can find a steadier way to live alongside forces we cannot control, preparing, grieving, and then, patiently, allowing new green to take root.